you probably wonder why you should listen to me, because who wants to deal with a psychiatrist? Yeah. However, when you look into history in the, when you were probably not even born yet, some of you, that in the 80s, the brain science looked towards the computer science. So there you had parallel distributed processing, connectionism, but however, then the computer people, the AI people realized, okay, maybe it's not as easy. And then the direction changed, that you looked towards the brain. And I think that it's even more relevant these days, because for your generation, the artificial intelligence is much more prominent than for my generation. And I actually get some students who come to me because I do all this mental stuff like sense of self. One student actually came to me from Japan, and he said, yeah, he came to me because when he saw a robot, and he was asking himself whether the robot has a sense of self. So, and I tell you, I hope that I can at least shed a little bit with my talk a light on why it is, what are the conditions, the kind of implementations you need to do in order for the robot to possibly have a sense of self. And even more important, why that sense of self might be even relevant for the behavior, because that's ultimately what for you guys counts. Whether you don't care about the self, obviously I do, but whether the self has a behavioral relevance for navigating in the world. So and I will show you some of the things. Some of you might know this movie, it's a Frankenstein, initial movie from the 80s. Highly recommend, you can download from your YouTube. It's an excellent movie and also very funny. And yeah, and what we currently in neuroscience, as much as there is progress, what we don't really understand is whether how neuronal activity transforms into mental activity. You could imagine the brain just processing without having any kind of sense of self, without any consciousness. And that's what I would claim is devices like AlphaGo or others are like that. They have a lot of processing capacity, but there is absolutely no necessity for these devices to develop consciousness, meaning their intrinsic design it's completely independent of self and consciousness. So that, reversely, that raises the question for the brain people, what is the brain's design like? Its inner basic processing features, what kind of coding is the brain's activity like, such that it cannot avoid producing consciousness and sense of self, because nobody can avoid that. We all have consciousness, at least I think so. Yeah. So, and I start, which is very important, as you're an engineers, most of you I assume, so you know it's very important the kind of model you have. The kind of model you have has strong impact on how you actually realize and design your device. And for an experimental neuroscientist like me, the kind of model of brain I presuppose is very important for the kind of experimental designs I do and the way of analyzing the data. Lynn knows some of that because he already worked with me. So I show you, and this is probably very simplistic now, model of a car, but nevertheless consider that I'm not an engineer. I'm very naive to that. So the first model is really the predominant model of the brain these days. The brain is like a car. So it's purely mechanical, purely linear, and it's basically, I always like to say, I know it's not that easy, but nevertheless, the strength, the degree to which you push the gas pedal directly, proportionally, linearly corresponds to the speed of the car. Yeah? So you have a direct linear relationship between the strength of the gas pedal push and the speed of the car. And that's basically the way neuroscience often these days, and also in the history of neuroscience, considered the brain. So you give a certain stimulus, like here, or a certain task, and then you elicit some activity change here in the brain, and then we call this stimulus evoked or task evoked activity. Yeah? So this is a gas pedal push, this is the speed of the car. And in this way, say you assume a direct linear relationship between gas pedal push and speed of the car, you assume a direct linear relationship between the activity change here, stimulus, evoked activity, and the stimulus. So, and then if you say that this is sufficient for this, then you say, why on earth do we experience this one in terms of consciousness? Why do we experience, okay, this has nothing to do. When you hear this talk, you say the psychiatrist, he's all nuts anyway, so I don't listen. It has no personal relevance for you, what I'm saying. Yeah? So then, of course, the question comes, is almost by default, why on earth, where do consciousness and sense of self come? Because you perceive the stimulus in relation to yourself, and you have a consciousness of that stimulus. But when you just consider this linear relationship, there is no place for that. So where on earth does it come from? Then people assume some add-on processes, some special additions. I don't want to go into this information integration, neuronal workspace theory, and so on, blah, blah. I don't want to go into it. But still it doesn't work. So there we have a real problem. So then there's an alternative model of the brain, which was sort of more on the sidelines in the history of neuroscience. But it's still sort of more on the sideline, but it's gaining more prominence, and I really try to develop and push that model. The brain is not like a car. Meaning, imagine you get out and it's not yet a self-driving car. So when I'm looking out here on the parking spot, all the cars stand still. Imagine it's the opposite way, all the cars move. Yeah, they move constantly around in certain patterns, and as I said, it's not yet self-driving cars. So that's basically what your brain spontaneous activity does. So the brain has an intrinsic activity, independent of your gas pedal push, and it's continuously active, and it continuously moves in certain spatial temporal patterns. So imagine when you play tennis, I'm a big fan of Roger Federer, and before when he waits for the service, let's say from Rafael Nadal, he's moving. He's moving in certain spatial temporal trajectory and pattern, and that's very important then how he can actually receive and return the service. That's what your brain continuously does. So meaning the service from Rafael Nadal just modifies the ongoing movement. Very important, you will see that comes back. So that is now the model of the brain which I presuppose and coming more. So you have an intrinsic activity of the brain, you have spatial temporal pattern. And we haven't understood these spatial temporal pattern, not at all. So one of the reasons why I'm turning and looking towards the engineers that you have a lot of signal processing tools to describe spatial temporal pattern, different forms of entropy, complexity, I don't need to tell you. And the second thing, so we don't understand the nature of the spatial temporal pattern. Second point, we don't understand what is the role of this spatial temporal pattern. Why on earth? The brain invests a lot of energy. 80% of its energy goes into this one. The stimulus processing is just 5% increase. So the energy is here in this one. So this must be important biologically. Yeah? So in the spatial temporal dynamics. So that's the second rule. Why on earth does the brain this? My assumption is that these spatial temporal dynamics is central for mental features. So and that has a very radical consequence that mental features like sense of self or consciousness are spatial temporal features. They are spatial temporally dynamic features. They are not features of some kind of mind or some kind of features of a specific higher order cognitive process and so on. They're very how the brain constructs its own space and time, its spatial temporal pattern. And then of course the question arises, so how is it possible when you look at me, you have your spontaneous activity here, and then how does your spontaneous activity need to interact with me as a stimulus in order that you can perceive me conscious, that you have consciousness of me. So meaning the content, I'm the content for you, must be somewhat associated with consciousness. And that's exactly that. So then the question is, how does this, the spontaneous activity, interacts with the stimulus? Yeah? So how, and even more pronounced, how does the spontaneous activity must interact with the stimulus in order to associate consciousness with the task evoked activity. So that's the overall background, and consciousness, as you also know, comes with a certain sense of self. So when you hear me, oh God, that's completely boring, he's always telling these old stuff and nobody's interested in. So it has no personal relevance, it doesn't touch upon yourself. So when you forge also yourself, it comes into the equation. So in my talk, will be exactly about what we call this, meaning the interaction of the spontaneous activity with external stimuli. These are basic mechanisms, and I do think that these mechanisms are highly relevant for how you design your devices. First, your device must have a certain spatial temporal structure, which is very dynamic, an intrinsic spatial temporal dynamics, and the nature of that dynamics we haven't fully understood yet. But I'm deeply convinced you need that. And second, you need that spatial temporal structure needs to interact in a certain way with the stimuli, in a non-linear sense. Very important. You will see that comes down towards the end of my talk when I present you a set of experiments. So non-linearity is an essential feature. So we are dealing here going into dynamic systems theory. It's a very important feature, and I'm aware that I do not properly define non-linearity here because I'm not an expert. We're trying to work on these kind of things. So I focus on this one and the mechanisms, and I show you basically two parts in my talk. First, you really want to know, is the resting state or spontaneous activity, is it really relevant for mental features? So first you need to show, does spontaneous activity predict mental features? That's the first part of my talk. I will show you some of that. This is, as I said, this is really a new field. In recent years, more and more data come out that the spontaneous activity predicts behavior. And we also have a lot of studies showing that, and we particularly focus not only on behavior, but on mental features like consciousness and sense of self. That's the first part. I will show you a couple of those things. And then in the second part, which is probably the more interesting part for you maybe, some of the mechanisms of how the spontaneous activity interacts with the stimuli and how that is modulated by the different stimuli. So I start with this one. And I lead you to a study which was done by, so here, I don't need to show you this one, you know all this. The brain fluctuates, the activity of the brain fluctuates, it's very dynamic. It has different frequency ranges, and you all know this. We call this gamma 40 to 800 hertz, beta 13 to 30 hertz, alpha 8 to 13 hertz, theta 5 to 8 hertz, delta 1 to 4 hertz, and we call this infraslow frequency from 0.01 hertz to 1 hertz. So you don't need to know all this. This is faster frequency, this is slower frequency. What is important, we can measure these guys with EEG or magnetoencephalography, and we can measure these guys with fMRI, magnetic resonance imaging. And yeah, and I sort of walk back and forth between these different frequencies. Mainly I focus this one, but I will show a couple of studies on this one. So this is very important, which frequency range you target, and obviously the different frequencies have different roles. You will see this in my talk, that the different frequencies have different role in the interaction between resting state and stimulus. So, and now I show you a first study. What we did, it was done by a postdoc from Japan, Takashi Nakao. So he was interested in decision making, and he came from Japan to my group, and I never worked. Decision making is a huge field in neuroscience, how you make decisions. And I never worked in decision making, so I had no idea why he wanted to come to me. So it took me 2 years to understand that. Because what he was, yeah, you have to figure out why the people want to come to you. Yeah, so it took me 2 years to figure out. And he was interested in how our sense of self impacts our decision. Because we all know we have sometimes very more subjective decisions, more objective decisions. And then, particularly, he was interested in this self, and this was a very clever idea he had here, that there are certain decisions where you have cues where it's very clear, which basically the cues itself give you a certain idea which to decide. Let's say if you have the choice between $100,000 and $10, it's probably clear which one you will prefer. Yeah. So that's what he called externally guided decision making, because if you have 100,000 versus $10,000, yeah, it's clear, it's very clear where you have more reward, so you will choose 100,000. However, if you have let's say if you have in both cases 100,000 and it is associated with not with different rewards, or let's say you have 10,000 and 100,000, but now you need to choose which profession you want to associate with, then it's not as clear, because then you have a personal preference. I show you that in the next slide here, what he did. So it's basically, you have two professions, and here you have accountant versus tax clerk, and you have to make a decision which one earns more. So there you have a clear external criterion, because you know maybe the accountant earns more money than the tax clerk. So that's an externally guided decision, where you have criteria within the terms itself which guides the decision. And these are external criteria. So he said that externally guided decision making. And then, or you can also do, for instance, which one occurs more often. Yeah, if this occurs more often throughout the paradigm, it's clear you have high frequency, this occurs very often, very less. So you have sort of external criteria upon to decide between these two guys. However, if you need to decide which one you prefer personally, then you don't have an external criterion anymore. It's internal. It's your subjective preference. So if you want to say, so this is more external, this is more internally guided. So obviously, this one involves yourself. Yeah. Maybe despite, so here you say, yeah, I want to be, so you have no external criteria. It's just your internal subjective preferences. So that's why he spoke of internally guided decision making. So the question is, and then some other stuff which I don't want to mention here, and he did this in an EEG study. What I show you here, again, I don't want to go into detail here. He had a conflict-related negativity, CIN it's called. There's an N2 potential, a negative potential, around 200, 300 milliseconds. And she showed some differences between internally, externally guided decision making in that potential. Now the question is, because in both tasks, you may remember that, he received exactly, subjects receive exactly the same stimuli. The only thing was the kind of decision, whether these stimuli occurred more frequent, which one of these occurred more frequent, and which one you subjectively prefer. So where does this difference come from? You see the neuronal difference here, and now I show you the next one. What we show here is then he correlated the event-related potential with the resting state in those subjects. And what he observed, so here on the y-axis you see the degree of the amplitude of the event-related potential. On the y-axis you see the power in the resting state in the different bands. It was an earlier investigation, so we hadn't the kind of measures we have now at the time. So and what he observed was very interesting. So in the externally guided, we had absolutely no correlation of the resting state with the event-related potential. Yeah. So the event-related potential must have been just caused by the stimulus itself, independent of the resting state activity. However, when you look to the internally guided, when you had to basically describe your personal subjective preferences, then you suddenly see a very good correlation that the degree of amplitude of your event-related potential is directly predicted by the resting state. So that means that maybe your resting state contributed something to the event-related potential only in the internally guided, when your subjective preferences come on board. Whereas in the externally guided, they don't contribute. So it's basically, in both cases, you see a task evoked or stimulus-induced activity, and two event-related potential, but it basically seems to be constructed by more by the resting state, has a stronger impact on the internally guided, whereas in the externally guided, it's just the stimulus itself. I'm sure some of that sounds resonant with you. So And he made a very nice figure at the time on this, which he did here. So we have basically different kinds of situations. We have an external criterion like, okay, does this occur more often or less often? But however, we have many situations in our daily life where we don't have external criteria, or where we don't have the time to think about this. Yeah? So then we remain ambivalent. And the only way for us to make a decision is go internally, think about our sense of self, internally guided. And that's interestingly what we describe here on the behavioral, psychological, or situational level as externally and non-external, seems to be also mirrored then at the level of the neuronal activity. That the internal activity of the brain itself, the resting state, helps us to provide sort of a criterion to make the decision, internally guided. So yourself, your subjective, helps you to make a decision. Whereas in the case of an external, the resting state or spontaneous activity doesn't contribute, and it's just more driven by the stimulus itself. Yeah? So, and you will see that, so keep that in mind, even if you don't understand the detail, but the main distinction here, there's an internal, more internally guided, self-related, externally, more situation, external criteria. And so, keep that in mind. Now, this study was an earlier study, we published it in 2013, and that was really a hint that maybe the resting state makes a specific contribution to particular our sense of self or self-relatedness. What do I mean by self here? You look into the mirror every morning, I assume so, and yeah, you recognize yourself, and also you have a certain feeling, yeah, this is me, this is myself. So, and usually you're not aware of that, because you take it for granted. However, all that may change when, for instance, you have certain psychiatric disorders like schizophrenia. Then you suddenly do not experience yourself as anymore. You see you in the mirror and say, no, this is not me. And then in extreme cases, you can also take on the identity of another person, usually famous people. I met a couple of Jesuses. In China, I met Chairman Mao, not the real one, yeah. But I didn't tell the patient, yeah. And actually, back in Germany, it was very funny. On one of the wards where I was in charge, I had two patients who at the same time said they were Jesus, and they dressed like that and everything. Mm-hmm. So I asked the one patient, there is a Jesus here. Do you know? Yes, of course, yeah. And you know how many Jesus were there in the history? Only one. And yeah, and then I asked him, then how is it possible there's another Jesus here on the ward? He said, the other one is wrong. And then I asked the other one, he gave exactly the same answer. So these people are really convinced they are Jesus. Yeah? They have a certainty, and the certainty is a feeling. Yeah? And that's your sense of self, because that gives you a certain a certainty, a sense, feeling, and you're convinced about it. Yeah? It's very important. So, so far, and now I give you another example. So this finding was one of the findings where we said maybe your sense of self has something to do with the internal neuronal activity and the spontaneous activity and its spatial temporal pattern and dynamics. So now I show you an example of that. Now we go from the upper ranges of frequency ranges from EEG to the infraslow range. And I'm a big fan of these infraslow ranges. Why? Because first they have more power. I don't need to tell you, this is scale-free activity. They have more power, and they have much longer cycle durations. This is 0.01 Hertz, is 100 seconds, so you can integrate different stimuli. You can put them together or chunks them together. So I show you now one fMRI study which we published last year. So what we do here, we measure fMRI. This is a frequency range between 0.01 Hertz and 0.1 Hertz usually. And so this is a raw signal, then we do a fast Fourier transformation, and then we do a power spectrum. I can show this. here, typical power spectrum, frequency, power, I don't need to tell you. And what you also see is this, each line is individual subjects. What you already see, you see a lot of inter-individual differences. And so this is not an artifact. This is an intrinsic inter-individual differences. And of course, where do these inter-individual differences come from? Most likely because each individual is, has grown up in a different context. So this is a central criterion for your artificial devices. They really need to show inter-individual differences. Yeah? And they need to be context sensitive. So this is not written in stone. This can change over the time. There are cultural differences. We do trans-cultural comparison. So this is very important. Yeah? That's why your sense of self is different from mine, and your spontaneous activity and its spatial temporal pattern is different than mine. Very important. So, and then you know all that we do a log-log transform and we get a scale-free activity, and the spontaneous activity in the brain does indeed conform also to scale-free patterns. Another thing, I will show you later the data, we do also some autocorrelation window. So, and then the question is whether the temporal structure of the scale-free activity is related to your sense of self. So here we measured the sense of self with the self, what we call self-consciousness scale, which has different, basically asks you different questions. Are you focused very much on yourself? Do you have a lot of daydreaming? Or are you interacting more with other people? And questions like this. And it has 3 different subscales, as we call them, private, public, and social. And to our, so first then we did the scale the power spectra for certain regions in the brain, in the middle of the brain. This is medial prefrontal cortex, posterior cingulate. The middle of the brain has been shown to be associated with the sense of self. And you do the power spectrum, you see quite differences. You see also differences in the power spectrum between the different regions. So this is another, just 1 second, one important feature which you probably need to build into your artificial devices. You need to have different modules, and each module has a different spatial temporal dynamics. So we're currently engineering a large brain mapping process where we try to, for each region in the brain, we try to determine a certain spatial temporal readout or pattern.
So this spectral function there, how reproducible is it for a given subject, let's say from one day to the other, compared to the spread from subject to subject?
Yeah, good question. We haven't done that yet. We have now currently the data set, a publicly available human connectome data set where we can test for that. The intra-subject variation is much, that I can say already, the intra-subject variation is much lower than the inter-subject difference. So there is a certain stability to it. It seems to be somewhat of a trait variation. Yeah? But it's not, it's very tentative. But the inter-individual differences are huge, and it's not artifact. Because usually when you consider this kind of data, you would say, wow, you did bad pre-processing, it's very noisy data. It's not, it's intrinsic. Yeah, and that's central. That's really, really central. Yeah. Okay. Then we correlated the power law exponent of the resting state with your sense of self, and particularly here for this region, we got a very good correlation, particularly for private self-consciousness. Yeah. So meaning, and this is important, the higher your power law exponent, the stronger your degree of private inner self-consciousness. And as you know, the power law exponent in this case is mainly driven by the slower frequencies. Yeah? If you have strong power in the slow frequencies, in the long cycle durations, then you have a higher degree of private self-consciousness. And in a way, when you consider that from a common sense point of view, it makes sense, because you have longer cycle durations, more power in the slower stuff. You have more temporal stability, temporal continuity, and that what you experience also on a mental level. Yourself is sort of somewhat stable, continuous across time. Yeah, your mental self, not the body changes all the time. Yeah. So now, if you say there is still I showed you so far how the resting state, which we acquire in 5 to 10 minutes or longer, predicts some mental features like internally guided decision making or a sense of self-consciousness. Then the next question is now, how can the resting state impact task-evoked activity? So one step you would say maybe prior to the onset of the stimulus, what we call pre-stimulus must have an impact on the stimulus. Prior to the stimulus is pre-stimulus activity, and that somewhat must reflect the ongoing spontaneous activity pattern. So this is what we tested here. So this is again the EEG study. So here we did, I show you the design, it's maybe the easiest. What we do here, so here we presented emotional stimuli, and people had to judge whether they perceive the stimulus as high self, as very related to themselves, or as low self, and not at all related to themselves. And then we looked for what happened prior to the perception of the stimulus. So we grouped all these items here for high self, low self, and then compared the high self pre-stimulus period versus the low self pre-stimulus period. So that was the main idea of this study, because we wanted to see whether the pre-stimulus activity level has an impact, predicts whether you can perceive the stimulus as high self or low self. Yeah? So, and if that is the case, then you would expect that maybe prior to the onset of the stimulus, your pre-stimulus activity already encodes some information about low or high self-relatedness. And here I show you first event-related potential. You see some differences between high self, low self, which makes sense. It's a P300 here, very typical. So this is in line with the finding post-stimulus. But the real thing, we were interested in the pre-stimulus activity. So we did an event-related spectral perturbation. Here you can see the different frequency ranges, and here you can see the time. And this is important. This is prior to stimulus onset. Yeah. So here is stimulus onset, minus 500, minus 1000, minus 1500. And what you particularly, and this is all the pre-stimulus periods for low self, all the pre-stimulus periods for items that were subsequently judged as high self. So, and what you can see here, a significant difference, particularly in the range between 7 and 10 hertz, which corresponds to the alpha, what we call alpha frequency range. You can see this here. You can see much more alpha in the high, in those items which were just judged as high self here, when compared to those that were judged as low self. So this tells you that maybe your pre-stimulus alpha is very important and somewhat encodes some information about whether you will perceive the stimulus as high self or low self. Yeah? That also gives you about the neuronal marker. We will come back to that. Here you can see the overall topographical map of this interval with minus 500, and you can see there's a clear difference in alpha. The more red, the more alpha power. Yeah. I think I leave that out. And so that really raises the question about the sense of self. We have many other studies on the self. I don't want to go into that. But that the self might be really a certain temporal dynamics, consist in a certain temporal dynamics and spatial dynamics. So that the sense of self is encoded in a certain spatial temporal pattern. Yeah? I showed you the scale-free activity. Here's the pattern, the relationship between faster and slower frequencies. The scale-free findings, we have a paper which we're just about to submit. We replicated them on an EEG level. And we also saw that the autocorrelation window predicted your private self-consciousness, meaning the longer your autocorrelation window, the higher your degree of private self-consciousness. Yeah? So it tells you that maybe what we experience mentally might be characterized by certain spatial temporal features which we can measure with some of the tools you have in signal processing in dynamic systems theory. So that's why I come to the conclusion that I consider the self a spatial temporal feature. So what does this now imply for your devices? That I would say for AA, you need a certain spatial temporal pattern. And this spatial temporal pattern should have corresponding values in autocorrelation window, in Lempel-safe complexity, in spectral entropy, in scale free to the brain, in order to optimally interact with us. If you want your device to interact, let's say, with other species like monkeys or bats, then you should probably have a different spatial temporal pattern with different scales. So your scaling is extremely important. Yeah? One line of research which we're currently doing is that we try to get more into the scale-free activity and apply other measures. Because I think the scale freeness is important. Ultimately, what your mental features, you perceive me now as a content of your consciousness, but you perceive me against the background of other people, the whole room, and here's the outside thing. So basically, your mental state, me as content, I'm nested within your ongoing brain activity. Yeah, it's like I always like to have this example of the Russian dolls. You can predict, so the different Russian dolls, you only see the large one from the outside, but you can already predict from that whether you can predict the shape of the smallest one, despite the fact that the size of the smaller one is very different. Of course, it's not as simple in the case of the brain, but it's self-similarity and the fractal nature. So this is why we now explore further other fractal tools and other tools for scale-free activity and related that to sense of self and mental features. And I would argue that that is central for your device. If you have a device with the scale-free properties and the frequency range, which is completely different than the one of the brain, that device will not well interact with us. Yeah? If you want the device to fulfill task and frequency range which are beyond the brain, you want to have tune the frequency range of your device that it overlaps with the one of the brain. And you need a scale-free distribution or autocorrelation window. We have very good results with the autocorrelation window. Also, we have a recent study now, again, about almost ready for submission, that the autocorrelation predicts your internally guided decision making. Yeah? So temporal continuity, the different kinds of temporal measures are central. Yeah? So that's something you need to, basically you need to create an inner time for your device. In my language, you need to have an inner time consciousness. Yeah? And that you can do by getting into the spatial temporal dynamics. Yeah? And then probably this internally, externally guided decision making, I think, is a wonderful example how that is really relevant, because we have this situation in daily life where you're very ambivalent. We don't know what to do because there are no external criteria. And as a psychiatrist, I can tell you, if we are lacking this internal criteria, your sense of self, we cannot decide. So schizophrenic patients, they stand in front of the room and they don't know whether they shall enter or not. Because there's no objective external criterion. They themselves have to decide. They have no sense because their sense of self is gone. Yeah? We call this ambiguity. So I had patients standing for half an hour, shall I go in, shall I go not in? Yeah? Because there's no internal criterion. And the door itself doesn't provide an external criterion. Yeah? Sounds banal, but it has major implications. Yeah? Okay. So just on a more modern conceptual level, the self, you might know this from philosophy, has been always assumed a higher order cognitive function. You need a specific module to build in a self module to build into your artificial device. I say no. Your self is not a special module within the device. Your self must be created in the overall spontaneous activity and spatial temporal pattern. And that is the very basis of any kind of processing which goes on. Yeah? Yeah, so that's basically here. What I didn't mention, how the spatial temporal pattern is created, that's strongly context sensitive. upon your environmental context. I don't have the time to present those kind of studies. Okay, I hope that gave you some kind of idea why the spontaneous activity is relevant for me. And mainly if you say, okay, I don't understand all this, but if you just have two things as your take-home message here, spontaneous activity has a certain spatial temporal dynamics, which Dr. Northoff desperately tries to characterize with some of our measures, which he doesn't properly understand. And second, this spatial temporal pattern somehow seems to be relevant for mental features like sense of self, what I showed you here, and also for consciousness, which I haven't showed you here. You can look on our website. There are plenty of data and I have all books and papers on that. So now I come to the second part of my talk, the more mechanistic part. So if the resting state is relevant for mental features, and mental features go along with task-evoked or stimulus-induced activity, you would expect that your resting state somewhat interacts in a specific way with the stimulus. So we called this in an earlier paper, 2010 here, rest-stimulus interaction. And that raises the question, how must the spontaneous activity in its spatial temporal pattern shape and impact the stimulus-evoked activity such that the stimulus-evoked activity can be associated with consciousness? I will only address the first part of that question, meaning what are the mechanisms of how the spontaneous activity interacts with the stimulus? I leave out the second part because it's beyond my capacities at this point in time. Why and how that interaction is associated with mental features like self and consciousness. So that I can come back in 3 years and I can tell you more about it. Then we have the studies from. So, and this is the topic. Remember the two models of the brain. When you have a purely linear model, remember brain is like a car, this question doesn't arise. Because you say, even if there's spontaneous activity, it's just a linear relationship between stimulus and stimulus-evoked activity, so this question doesn't arise. Yeah? And exactly that's the situation in neuroscience. People don't ask this question. However, if you have the second model, and there are a couple of single investigators who address it, then this question becomes very relevant. Because then you really need to know how does the spontaneous activity interact. So, I show you again, very briefly here, the typical thing here. You see these are three different models of how they could interact. So, you see here, these three colors are different lines of resting state activity levels. Yeah, it's schematic, but here. So, and then here you have these three different levels of activity and you have a stimulus coming. The traditional model is this. You have a stimulus coming, the activity raises, and the stimulus always induces the same degree of activity. Yeah? Remember what I said, there's a linear, sufficient relationship between stimulus and amplitude. That's what you see here. So in all three cases the same thing, but you measure different levels because you have different levels of spontaneous activity. Yeah? So basically when you have three different heights of this floor, I'm basically always the same size, yeah? But you measure me differently because the floor is high. This is it. So we call this pure linear superposition or additive. The stimulus-evoked activity is just added on to the ongoing spontaneous activity. Then there's another way, that your spontaneous activity levels impact how the stimulus is processed. Meaning they might either give a boost or attenuate the stimulus. Here, the green one you see in attenuation. Yeah, you have already a high stimulus in resting state activity, and then it's not much. The stimulus cannot induce much more. This is not just a ceiling. Yeah, and then if you get lower stimulus-induced spontaneous activity, you have the highest. So here you can see a clear impact, and this can be called negative or non-additive model. And just a mirror image of this is this one. You see this level can induce, is predisposed to show the highest stimulus-induced activity, whereas this one is the lowest. So this is a positive, but also non-additive interaction. So now the question, which of these models holds? Yeah? So basically the rest of the talk is just about this. Yeah? And I will show you, at least from my point of view, some very interesting results. Yeah? So now I report you 2 lines of data. One line of data from fMRI, so we are in the infraslow range, between 0.1 Hertz and 1 Hertz. And the second data is from EEG intracranial, which is Ning and Lin we analyzed in the second step. So this one was done by Rui Huang, as you can see, Chinese name. He was a former postdoc of mine, he's now in Michigan, and we discussed this. He did an fMRI study, very clever design, and I walk you through some of those results to show you some idea. And again, just a sidestepping, why is this relevant? Because you need to show in your artificial devices, you program them, you give them a certain spontaneous activity, and you can also program how they may or may not interact with the external stimuli. And even for your BCI, it's very relevant, because what you do with BCI, you impact the stimulus. Yeah? So that's very important, how and whether that interaction is associated with perception or consciousness or not. So I'll show you here some of the study. So this is for the fMRI. So basically the main question is here, you see what we observe, and I will show you more of that. So the traditional view is just the stimulus is measured by the degree of amplitude it elicits. However, what we observe, and usually what you see in the imagings in EEG, fMRI, is an average across different trials. So you put 100 trials together, and that's basically your mean average is the amplitude. However, what we observe, that across trials, you have a variation in the amplitude. And that's very strange. You present one and the same stimulus, and when you have a purely mechanistic view, that one and the same stimulus should always induce the same amplitude. That's not the case. So where on earth is the variability of the amplitude coming from? So we call this trial-to-trial variability, and we can measure, for instance, the trial-to-trial variability by measuring the variability at each time point and in relative to the variability at stimulus onset. Because obviously the assumption is that the trial-to-trial variability can only come from the pre-stimulus or spontaneous activity, not from the stimulus itself. Yeah? Because the stimulus is always the same. So the only other possibility is from your pre-stimulus or spontaneous activity. So that's why we measure the post-stimulus variability in the amplitude against the variability at stimulus onset. And that has been shown, interestingly, by Churchland et al. On the cellular level, single firing rates. Then Bejuhe showed it 2013 in fMRI. We had another paper in for fMRI 2015, where we showed that the trial-to-trial variability is related to another mental feature to your subjective experience of space. It's called peripersonal space. So that shows, look, trial-to-trial variability is very relevant for mental features. That was an fMRI. And then we showed now in this paper more of the mechanism. So, and then of course we were interested in how does the spontaneous activity and the pre-stim interact with this trial-to-trial variability. So, and what he did in fMRI, I don't know whether you have done fMRI, we presented a special fMRI design here where 2 seconds of stimulus and then a very long intertrial interval, because you will see this in the next slide. fMRI is a tricky one, like all imaging techniques. You can see you have here's the stimulus, you have an amplitude, and then you have what we call a long undershoot in fMRI. So until it returns really to baseline. So that's why we wanted this long intertrial, what we call intertrial intervals, 50 seconds. So you don't need to be concerned about this. It's more sort of a method thing. But what is important here, that we could really say then, okay, that we really have a proper baseline where we really know, even during the stimulation, the task, where we have a proper sort of resting state. And you will see we take this as what we call pseudo-trial. I will come back to that. So this is basically the interval which we took as a marker for the spontaneous fluctuation. For each trial we looked prior to the trial, and we look what is the spontaneously ongoing fluctuation. Because when you see the stimulus-evoked activity, it's a mixture between both the effects of the stimulus and the ongoing spontaneous fluctuation. And that's very important, because what we measure here is a hybrid between the stimulus and the spontaneous activity. It's like dancing a tango. Yeah? They always do, the couple is always together, and the one cannot do without the other, and the other not without the one. Otherwise, it's not tango anymore. That's exactly here. So this is the tango of the brain. And here I show you some fMRI data. So colorful regions, actually we presented here autobiographical and heterobiographical or self and non-self stimuli. Plenty of regions activated, and now each curve is here. This is the amplitude or stimulus-evoked activity. Side remark, you see the differences. These are the different regions. You see huge difference between different regions. So that's another thing which I think important. Each region corresponds to, has a different temporal spatial pattern. And as I said, we have a large mapping project now where we want to have for each region provided temporal spatial fingerprint. Yeah? And the heterogeneity, the plurality of that is very important. So you need to build into your devices large heterogeneity, temporal spatial heterogeneity, because that's very important. You want different time scales, different constellation of time scales available in your device. Yeah? And here we see the trial-to-trial variability. Typically, you have a reduction, trial-to-trial variability reduction. That's exactly what you see, but again, huge differences between the different regions. And then he calculated the so-called TTD index, which here doesn't involve the pseudo trials yet. Yeah, so it's slightly different from your TTD index. Yeah, and then I told you about the pseudo trials. So the pseudo trials are prior to stimulus onset, the spontaneous fluctuation. So he took a 10 seconds interval because it's fMRI. And that's what you can see here, the dotted lines. The dotted lines are the ongoing fluctuation, the pseudo trials. Because that still happens in the background of your ongoing stimulus-induced activity. So I talk to you, yeah, but still in the background, the guys still continue talking. So what I hear is a mixture between you talking and them talking. Yeah? Yeah? And then I need to disentangle that. So I need to tangle what is you and what is them. So they are the spontaneous activity and you are the stimulus. Sorry for degrading. Yeah? And yeah. So that's what he tries, and this is a very ingenious method to do this. I mean, this is really a clever idea. He came up with that. And so here's a spontaneous fluctuation. So this is basically your ongoing background noise. Yeah? And this is what you actually induce in me, but this is also the interfere with that. Yeah? And you can see, this is all a very important thing here. You can see if you have low pre-stimulus activity at stimulus onset, you see a relatively higher stimulus evoked activity. This amplitude, this difference is larger than this one. Yeah? So you see that the state at which your activity is at stimulus onset makes an impact. If it's low, the same stimulus will induce a larger amplitude than when compared to its high. Very important. Yeah? Same, when you speak loud or low there in the background, it makes an impact how I will hear you. So he speaks with the same voice, same thing. Yeah? Okay, and that's what he calls an low high index here. You can see this. So when you then set these guys to 0, yeah, then you get this. And you see the relatively high. Remember, that was the second model, the negative interaction model. Remember, I can go back. There's a beautiful presentation of that. It's this model. Remember, low pre-stimulus, high amplitude. So what we're currently doing, I do this together with physicists in Taiwan, that we try to develop a computational model for that. Because that's important. That's what we need to get more into the mechanism. And I would argue this is central for your devices. Yeah? Yeah. Okay, yeah. Then the question, why is there a difference? Why does this work? So then he went into next step. He did some phase analysis. So he did Hilbert transform of the fMRI data, which has not been often done. But it's becoming more prominent because it's different in the infra-slow range, 0.01 Hertz to 1 Hertz, because you have fluctuations, you have not a clear stimulus onset. It's easier for oscillation for faster frequencies. So it's a tricky one. And you can see here the time series, and it's a Hayward, and then you get the phase onset, and you know that a phase cycle is usually a trough and a peak. I don't need to tell you that, 50-50. And what is important from the neurophysiological side, the trough has been shown to be high excitable, the peak has been shown to be low excitable. So when a stimulus hits here, there's not much activity induced, whereas here it's more activity is induced. So this is neurophysiological evidence from the Sutherland. So, and then he showed exactly that. This is this one. So here now he did the same thing, the real trials, pseudo trials, and then he calculated the phase of the pre-stim high and pre-stim low, and then he calculated a trough or peak, whether at stimulus onset the ongoing phase was a trough or a peak, yeah, at 0, and how that impacted subsequent the amplitude of the stimulus-induced activity. So when you can already see when it was at the trough, it's the red stuff here. At stimulus onset, you see a much higher amplitude than when compared to it was as a peak. And that makes sense. Remember, this was the lower because it's a trough, so it's lower activity at stimulus onset, and this is higher, but it doesn't induce as much amplitude. So he calls this trough positive index, and then you can also in the phase fall and rise also makes a slight difference. But this really is the most interesting thing. So that suggests that maybe this negative or non-additive interaction is phase related. Yeah, we will come back to some of them. Then, at the time, and this is was over 3 years. This took a long time. So at the time, then we also did the resting state. He did again, you know, all this scale-free activity. Each line is one region. You see again the huge difference between the different regions. Yeah, intrinsic. Yeah, and so did the PLE power law exponent calculated, and then he correlated that with the trial-to-trial variability, with the phase index and the non-additivity index. And to my surprise, and also to his surprise, that all correlated. So your scale-free activity in the resting state, it was a separate measure, 10 minutes, predicted your degree of how much the amplitude was impacted by pre-stim. Yeah, it predicted the trough peak index. Yeah, and then also the trial-to-trial variability. So that means that your temporal structure, or temporal nestedness, as I like to say, in your spontaneous activity, has a huge impact on how it will react and process to the stimulus. So meaning what you need to do in your device, and if you want to make your device flexible, you need to bring in this inner temporal structure. I explicitly say that, and it must be variable. Yeah. Okay. So I show you a summary of that. So there seems to be really, remember, the negative model, the non-additive model rather than additive model. So that spontaneous activity and the pre-stimulus activity have an impact on how the brain can process the stimulus. Yeah? The same way if you have two people dancing the tango, it not only depends on the two people, that depends not only on the, a bad example doesn't work. Okay, good, forget it. And the second thing, that seems to be phase dependent. Yeah? So the ongoing cycle duration, whether it's in the peak or at the trough at stimulus onset, has an impact on how the stimulus will induce activity or not. And of course now we have other data where we show that in turn is also related to consciousness and perception. Yeah? And so it's in a way a contingency. Your brain is a purely stochastic organ. Whether it's in the peak or it's a trough when I see you, it's not only me impacting your brain, but it's also your own brain impacting you, how you perceive me. And that's contingency. If I come at the peak, you will not process me, you will not become conscious of me. Bad luck. Yeah? If you're by chance in the trough phase, okay, great, then you have to process me and you cannot avoid seeing me conscious. Yeah? sorry. Yeah, so that's an important thing. And the thing is that even the overall temporal structure of your spontaneous activity, scale-free activity, strongly shapes the degree of phase-dependent non-additivity. Yeah? If you have stronger scale-free activity, higher power law, more slower frequency, higher degree of non-additivity. And in a way that makes sense, your slower frequency have more power, so they can exert a stronger boost on your stimulus. That's the way I explain it in my naive terms. So, however, as you know, all research only raises questions, it doesn't solve answers. So this also addresses a lot of questions. So first, of course, you would like to have the same mechanism in faster frequencies. Yeah. So I showed it for fMRI, 0.01 hertz to 0.01 hertz to 0.1 hertz. Question whether it also occurs in faster frequency, which we measure in EEG. Then, second, you want to have a time resolution. So the time resolution in fMRI is notoriously bad. Remember when you saw it, one of the X lines there, it was about 5, 6, 10 seconds, so it's a catastrophe. Your brain operates in milliseconds, so you need to go to faster time resolution and also then you try variability. And then, of course, you want to also remember the beginning of what I said. How is this non-additive interaction modulated by the kind of stimuli? Whether you present an internal stimuli, like self-stimuli, remember the data from the decision-making at the beginning, or whether you present an external stimulus, which a non-self, like another person's name. So here, the next study, and I really have to thank the two of you, and particularly Lynn, who went through all the iterations of my ideas on this, who analyzed those data. So here we present data from which we applied, which we measured in Shanghai, and this intracranial EEG is basically the electrodes are directly implanted into the brain. This is done in epilepsy patients to find the epileptic focus. But for the research, it provides a unique opportunity to get a very good signal without the usual EEG noise and artifacts and the indirectness of the skull and so on. So, and what we did here, we had 10 subjects, and we took all 84 electrodes from this, which all show you later a very good trial-to-trial variability. And so the idea was now basically to test for the non-additive interaction in EEG, and even more important, that we applied own name and other name. The own name is obviously an internally related stimuli, or internally directed, because you're familiar with this. If you hear my name, it has nothing to do with you, so it's externally directed. Yeah? And given the hypothesis, and I'll show you some of that, so this is the slide. So the first thing, I think I can make the right away thing, so we confronted here with spontaneous activity, pre-stimulus variance, and then you see the time axis, then what happens, external stimulus comes, and that induces usually some stimulus evoked activity. And you can measure that with event-related potential, phase locking value, remember the phase dependence from the fMRI, event-related spectral perturbation, trial-to-trial variability. And that's the assumption that, given our prior findings, that the external stimuli, externally directed stimuli, like my name for you, might just directly impact this one. It might not impact this one. Yeah? Meaning the activity here related to this might not be modulated by this. Whereas the hypothesis, based on the findings, what I showed you, and then various other lines of finding, that self-related stimuli like the own name, empirical findings showed that they are modulated by spontaneous activity at pre-stimulus variance. I showed you some of those data. And then you would expect that maybe this one, the interaction of these two with the stimulus leads to the stimulus evoked activity. So basically, as we say, as the Italians say, you have multiple paths leading to Rome. Yeah? So one path is externally directed stimuli. Another path, and that goes direct impact, so I impact you directly. Whereas internally stimuli only, because they are so close related to your spontaneous activity, that maybe this one has a stronger impact here. Yeah? Remember, that was a similar model for the internally, externally guided decision making. We had the event-related potential here. The externally guided decision making was only here, but only the internally guided decision making was modulated by these guys. Yeah? And now we try to apply the same model to the context of the non-additive interaction. The hypothesis is that maybe here this non-additive interaction is very relevant. Yeah? So, and I walk you through the data. Here you see the typical event-related potential. So, and you see all the different channels. You see quite a variability here. Typical, you see sort of, probably comes close to some kind of N100, something like that. So nothing special here. It was a simple perception. Here you see the try-to-try variability, and you see a huge difference between the channels because the channels were all in different locations in the brain. What is typically, you see stimulus, the TTV was measured in relation to stimulus onset, and you can see a decrease in the variability induced by the stimulus and a return to baseline variability. Yeah? So the stimulus, from the perspective of the brain, is just a transitory phenomenon. It just modulates, mitigates, attenuates, enhances what is already there. Yeah? When you all talk here in the room, and I come in, some of you might look a little bit but continue talking, so I just modulate the ongoing chatter a little bit, but not more. Yeah? However, the degree to which I can, let's say, suppress you in your talk, that will be the degree to which you will put attention to, pay attention to. Yeah? So meaning I become more conscious of you. However, if I do not manage to suppress your ongoing activity, or if your pre-stimulus activity set is in a state, no, I don't let myself suppressed by this strange guy, then you will not become conscious of me. You're just going on with your internal stuff. Yeah? Then two other measures which Lynn did, so and this is important. One important thing which I wanted to point your attention, focus your attention. You see, look, the timeline is here. The event-related potential occurs very early, 100 millisecond post-stimulus onset. Look at the TTV. So the peak of the ERP, the negative peak is here, 100 milliseconds, very early on. Look at the peak of the TTV is 500 milliseconds. For the brain, 400 milliseconds is an eternity. For your consciousness, not. For the brain, is. So this is important. So this seems to be early impacted. This seems to be later impacted. Yeah? You will see this comes again and again. So next slide. You will see here the EISP. You see a high gamma. This is in a gamma range, high gamma range, which we can nicely measure with SEEG. And you can see it very early on, 100 milliseconds. Yeah? Whereas you see a decrease in alpha and beta, 8, 13 to 30 hertz, or 20 hertz, later. Starts at 200 milliseconds, goes on. Remember, this corresponds well to the TTV decrease, the peak, around 0.5. This corresponds to the ERP, yeah, the 100 milliseconds. Then he also did the phase locking value, so basically the degree to which the phase was locked at stimulus onset, which you would expect with the stimulus coming, the phase shift, and that's exactly what you see. So the phase was always at the same state at stimulus onset, and you see this particular in the theta range here is between 5 and 8 hertz. So then he did also the EISP, probably leaves this out to not complicate things. Then the question, how are these related to each other? Remember, the idea was particular focus here on the trial-to-trial variability, because that basically reflects not only the impact of the stimulus, but the interaction of the stimulus with the ongoing variability of the pre-stim interval. And here you could see that particularly the alpha, remember the alpha decreased starting from 300 milliseconds, and maximum of TTV peak reduction was 500 milliseconds, and you can see it's a positive correlation, meaning the more decreased your alpha ESP, the lower your variability. Yeah, the lower the TTV and the more reduction, the better the stimulus could reduce the ongoing variability. So basically your alpha, and that's known, it's like an entrance gate. You have to open the gate, meaning you have to lower the alpha for the stimulus to be processed. And the better it does that, the better it can suppress the ongoing variability. Yeah? So, and the same for beta, each dot is one electrode, so you can see the differences between electrodes. Then interestingly, remember the gamma occurred much earlier. Remember the gamma occurred 100, next one, here. Here was the gamma, here was the alpha delta, and the peak of the TTV, remember, was here 500 milliseconds. So really you have a temporal correspondence between alpha, beta, and TTV. That's why they correlate. But you don't have a temporal correspondence between the TTV and the gamma. And that's exactly what then also confirmed in the data, that you do not have any correlation between TTV and gamma. So that's a new thing, that really the TTV seems to be driven by alpha and beta. Yeah? So you see, now you see a differentiation between the different frequency bands. So how it is important to have these different frequency bands. And that's very important also if you want to construct some devices. So then I show you more. Then now, remember we also presented own versus other name stimuli. So now we differentiate between that, and interestingly the non-self, the other name, induced a stronger negative amplitude here when compared to non-self, to self, the own name. And that was significantly different. Then also for the TTV, interestingly, the red one is the non-self, the other name. The blue is the own name, is the self. And you could see that the TTV is much more pronounced, the reduction in the self. So meaning this, the own name was much better able to suppress the ongoing variability than the other name, because here it took much longer to return to basic. Yeah. So in a way, the own name can much more effectively interact with your resting state, and that makes psychologically you might have heard about what is called the cocktail party effect. You're on a party and you see there's a lot of noise, and you can barely understand the person in front of you, and suddenly way in the back somebody whispers your name and you immediately hear that. So you have a processing preference for your own name, and I assume that that is related to some of those mechanisms. So basically your own name can much better suppress the ongoing variability of your resting state. So then you hear it much better. You hear the own name rather than the chatter of your own variability, of your own resting state or your own thoughts. Yeah? Okay, then also we did the EISP, and you see some differences here. Interesting, this is not, we see high gamma for the self, induces much more high gamma, and also for the phase locking, which was again interesting, that the non-self shifted the phase onset much stronger than the own name. So you have a difference between different kind of measures. You have the early measures, like the phase locking value, which is and the event-related amplitude, the event-related potential ERP, which are more related to external stimuli, which makes sense. The earlier the stimulus measures, the more impact of the external stimulus because of temporal proximity. However, the longer it goes on, the more impact the ongoing activity operating in the background exerts. And that's then where probably and that is related to more impact of your internal stimuli / the own name. Yeah? So, then the next thing, so now, so far, we only demonstrated use stimulus evoked measures, positive. Now we want to know what is the impact of the pre-stim. Is this really an additive or non-additive model? One of the answers is here. So then remember the pseudo trial. So Lin did exactly the same thing. prior to each trial, he extracted 1 second, calculated the spontaneous fluctuation, and set sort of a virtual stimulus onset. And say, okay, this is the ongoing fluctuation. And this is basically down here in red, called pseudo-trial. And then this is the real trial, where the stimulus was really applied. And you can see this is the variability of the ongoing fluctuation. And this is expected, it's the same, there's a certain variability calculated for different frequencies. This is for broadband, this is for alpha. I think something got shifted here. Alpha, beta, and this is for gamma, this is interesting, this is for beta. This is for theta, this is for alpha, this is for beta, this is for gamma. And you can see then, when you compare the two, this is a pseudo-trial, the ongoing fluctuation of the pseudo-trial, and the ongoing and the modified, attenuated fluctuation of your real stimulus, and you see the variance decreases. And that difference is, of course, negative. So remember, the negative interaction is non-additive. Yeah? However, nothing is easy when it comes to the brain. In another frequency, so in the theta frequency, you see the strong in alpha, beta. However, here, in the gamma, you see the opposite. So here, your real trial increases the variance when compared to the ongoing fluctuation. So this is additive. Yeah? So this is a very interesting model here, that depending on the frequency, you have either more negative or non-additive or more positive additive interaction. And you can see this is statistics there. So I walk you to the next slide. Then the same was done for the self. And interestingly, the impact of the self on the ongoing variability was much stronger, if you hear, significant, than for the non-self, when we compared this. So that already tells you that the self more strongly interacts non-additively with the stimulus, with the spontaneous or pre-stimulus activity. And again, you see the differences here. Interestingly, for gamma, it was the other way around. The non-self interacted much more strongly with the ongoing gamma activity than the self. Whereas for the slower frequencies, particularly here theta, is really the self. So that already gives you an indication. Maybe the own stimuli are more related to the slower frequencies, longer cycle durations, whereas the other external stimuli, non-self, are more related to faster frequencies. And that is further confirmed when you see next correlation. So now another way of getting at that, the non-additive, is basically calculating the TTV, plotting the TTV index, subtraction, pseudo-trial versus real trial against the pre-stim variance. And you can see that the higher your pre-stim variance, also the higher your difference between real trial and pseudo-trial, and that means the higher your non-additive interaction. So that's really the pre-stim variance, and you can see this in the theta. You don't see this in alpha, let alone in gamma. So that really tells you that your pre-stim resting state seems to impact subsequent stimulus-induced activity mainly via the slower frequencies. Yeah, and that may be the fact because slower frequencies have longer cycle duration, so they have a higher chance of overlapping with the stimulus than faster frequencies. So then he did the same for the self, and what you can see, this is a pre-stim variance correlated with the post-stim TTV, and you can see in self you have a nice correlation, in non-self you don't. So that's exactly goes along with the very early findings that external stimuli like non-self are not as dependent upon the pre-stim variance. So shall you, I leave that out to keep things simple. And then we did also the resting state. So how much did the resting state correlate with the stimulus-induced activity slash the TTV index? So the two measures which then calculated was the autocorrelation window and the spectral entropy. First we plotted them against each other, negative correlation as expected. And then you see this here, that the autocorrelation window, the longer the autocorrelation window in your resting state, the stronger your TTB reduction. So you tell us how important your internal temporal structure of your device or the brain spontaneous activity is. Yeah? And so meaning the longer your autocorrelation window, the better in the resting state, the better the stimulus can suppress the ongoing variability. Whereas non-self, it was completely independent of that. The TTB for non-self was completely independent of the resting state. And we see similar results for spectral entropy. Here for self, positive correlation, no correlation at all. So I present you now some summary slides and then I stop. So summary one, how do we imagine stimulus evoked activity during internally directed stimuli like self or on-name? I told you different paths lead to Rome. Here, the two different paths are an internally directed path, / internal stimuli self like the own name, whereas there's an external path, the other name. So here's the internal path. So you have an internal stimuli. That processing seems to be strongly modulated by the spontaneous activity temporal structure, autocorrelation window, spectral entropy, and the pre-stimulus variance. And that in turn leads to some kind of non-additivity in the interaction between pre-stimulus and stimulus. So I spoke here of pre-post non-additivity. And that in turn gives you late stimulus evoked activity. Remember, the ERP was smaller in the self, and you have stronger alpha and beta decrease, and stronger TT. So in the case of the external, you see it's a direct pathway. It directly impacts here early stimulus-induced activity with stronger event-related potential, stronger phase locking value, stronger gamma. Yeah. And remember, this one does not have much impact, so this seems to be more additive. Yeah, which makes sense. If it's directly independent, this remains more independent of the resting state. But now of course the next question you want to ask, why on earth do these stimuli are not modulated by this? Hypothesis that the stochastic structure, the temporal structure of these stimuli is less similar to this one. So if I start speaking German, you probably hear from my accent that I'm a German, I cannot hide it, then you will not be able to communicate and interact with me, let alone non-additively. So I'm an external stimulus for you. However, if we speak English, we can interact with each other. So you can process me through this one, and then interact with me non-additively. And we together might develop some interesting ideas, or some crazy ideas. Yeah? Otherwise, with German, English doesn't work. Yeah? So same thing here. So this is something which we're currently testing now, that we look for the stochastic. So we apply the same kind of measures in your external environmental context here, in this one. Let's say entropy, spectral entropy, autocorrelation, etc. And of course not easy to prepare the stimuli in a proper way. And to this one. So the degree of matching between these two guys might then define or determine whether the stimulus will be processed as an external or as an internal stimulus, as self or non-self. And that has, and I would argue that that has also an impact, and I didn't show this, we have to show this, that this impacts your spontaneous activity. Because the more your consciousness, the more you interact here non-additively, the higher your degree of consciousness. Because we have one paper in revision where we show that the degree of trial-to-trial variability reduction corresponds to the level of consciousness. Yeah. So basically, when I start speaking German, you will not become much conscious of me, maybe for the initial minute and then goodbye. You will disregard me. However, when I start speaking English with you, we can interact and I will become, you will have a much stronger consciousness. Yeah. So there's the relevant, and you can interact with it. So this we had yesterday a beautiful example of that. So it's basically really a pas de deux. It's like a tango, it's always with two. So you also your external stimuli, you want them to be optimally tailored to the stochastic structure or temporal structure of your spontaneous activity, the wheelchair example. Yeah? So as a psychiatrist, what I'm intending to do is look at this one and see where the deficits are, and then present my patients with stimuli which are somewhat close in their temporal structure, but not the same way, to train, for instance, with music. Yeah? And the reverse way, of course, is a wheelchair. Yeah? You need to in order to have an optimal interaction between your brain and the wheelchair, you need to present the wheelchair with a spatial temporal dynamics which is somewhat akin to the spatial temporal dynamic in the individual brain. So you need to present the wheelchair with a different spatial temporal structure, autocorrelation, blah, 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 to me than to him. Yeah? In order for us to optimally navigate this thing. I think that's central. Yeah? Okay, now they make me stop and I'm almost done. Why shall we care? I hope at least I can say that the TTV and / the non-additivity has an impact on consciousness. If you don't have TTV reduction, you lose consciousness. That's very clear. This has been shown in 2 studies, Sugar and Island MEG study, and this is a study I mentioned from our group from Zeroy in anesthesia. Yeah? And there's a recent study in J Neuroscience which showed the TTV and EEG to be related to perception. Yeah? So the non-additive interaction is central. Now the next question, of course, and I don't want to go into that, why is a non-additivity, why is it important that the non-additivity is there to yield a stimulus in consciousness? Very quick answer. Consciousness, you experience something in consciousness that goes beyond the information provided by the stimulus. If you now put the stimulus into the larger spatial temporal context of your spontaneous activity, that's exactly. Something is added. It's expanded. So in our recent paper, we speak about temporal spatial expansion. And that temporal spatial expansion, you need to have the stimulus in your devices interact with the spatial temporal structure in such a way that the stimulus is virtually expanded. So even if I walk out of the room, you're still conscious of me. I hope so. Yeah? And meaning your brain adds something that I stay in your consciousness. So I'm already physically absent. But virtually / mentally, I'm still present. That can only come from your spontaneous activity in the non-additive. And that's important. Because by that, the brain can manipulate its space and time and can better work with things. It can impact. Yeah? And I would argue that's central for the kind of devices I meant here. And that's the end of my talk. You see some of that in the book I wrote and a more simple book in this. And if you want to know more about it, look on our website. Thank you very much. And also thank you for this.
Any questions? Yes. I was going to ask if there was any kind of correlation between the activity of sensory and working memory processes and this kind of relationship, this kind of non-additivity that you see with these infraslow frequencies, these internal and external stimuli.
Yeah. I mean, would be separate experiments we didn't do, because it was basically. But you mentioned something which I really envisioned, that working memory is not cognitive but spatial temporal. Yeah. When you look at the frequency ranges of so I tackle these kind of cognitive tasks now in terms of a temporal view on what kind of frequencies. And indeed, we currently try to do this in the Human Connectome project. It's a large open access fMRI data set with resting state and tasks, and includes also working memory tasks. And we try to predict the working memory evoked activity and the behavioral performance by the spatial temporal features in the resting state. And ideally, you would like to have different measures like complexity, spectral entropy, predicting different tasks. Yeah, because each of these measures something slightly different. I'm still trying to figure out what you guys are doing. You just do some mathematics. For you, it doesn't matter. You just want to measure. But for me, it's very important what the exact difference is between these measures. And when I look into the literature, there's not much known about the relationship between these different measures. Like I showed you the correlation between autocorrelation window and spectral entropy. Yeah, but for me it's very relevant. Are they the same? What do they measure different? Because they might reflect some different spatial configurations on the psychological level. And that might be related to different cognitive tasks. Yeah? I hope that addresses, I cannot give you data on that, but gives you an idea. It's a spatial temporal view on cognition, spatial temporalization. Yeah.
Has any of this work been done on individuals in comas or vegetative states?
Yeah, so some of the, it's clear that We had just a paper in anesthesia, loss of consciousness, where you see a decreased scale-free activity. And we also measured variability in that. And interestingly, the spatial pattern of variability remains the same. On a lower level, the variability amplitude, the variability was reduced, but the spatial temporal relation between the different regions or voxels remains the same. However, what did not remain the same is the pattern of the scale-free activity between the different voxels. So, and from that, or regions, and from that we conclude that the temporal structure measured by scale-free activity is central for the presence or absence of consciousness. Yeah? That's why I'm emphasizing temporal structure. It's not just the absolute value. It's a certain organization, form, whatever term you would like to use. Yeah? It is not, and that I think is the beauty for me. It took a long time for me to understand the scale-free activity is the relationship between the power of the different frequencies, relative. Yeah? And ultimately that's, when you trace it down to very basic fundamental principle, that's what I mean by different space code. Yeah? You will see this in the introduction to volume 1. It's the relative changes. It's not the absolute activity in one region. It's the relation of that activity level to the other. So the same level of activity can mean something completely different if the other region is different. And that's behaviorally and mentally relevant. That's what I mean by different space code. Yeah? That's, in order for your device to have consciousness, I'm very clear and very bold in my hypothesis. You need to have different space coding. Stimulus-based coding, just coding of the absolute power or one particular discrete point in time will not work. Yeah? When you look into nature, I cite some of those examples, you see a lot of different space coding. Yeah? Why is that? Because your brain is a stochastic organ. So it always encodes one time point in relation to the next other time point. Yeah? And that creates, ultimately, when you have different frequencies available, like the human brain, a certain temporal structure by default. Yeah? Of course, now you can say with your artificial devices, so the human brain, to be honest, I really don't know. What is the maximum and minimum frequency range of the human brain? I don't know. I'm very embarrassed to say this because I should. I cannot find literature on that. It's clear that, for instance, other species, like the bat, they can process ultrasonar wave. We can't. So that's very important, the range of your frequencies for your device. And also then the fine-grainedness of your frequencies. And the distribution of that. So it's not just the absolute range. If you have only, let's say, 1, 2, and 10 hertz, you might have the same frequency range as somebody who has 1, 2, 3, 4, 5, 6, 7, 9, 10 hertz, but the second one will be much better functioning than the first one. Yeah? Very important. And then, of course, you need, definitely, if your device is not scale-free, it will not work. This, I predict that, without knowing too much about this. Yeah? Because you need the scale-free properties to adapt to the different time scales in the world. You're nesting in that. You have a certain, I would argue that our brain has a self-symmetry, fractal nature with the larger spatial temporal scales in the world. That's why we can somewhat access them and measure them indirectly. If that were not the case, like when you're vegetative, you can't. And then you don't behave anymore.
Other questions?
General questions. So how to define the spatial temporal structure or external environment, like objects, and how to map that to our brain's temporal spectral structure?
I don't know whether we had, so we're doing that, Mershad in my group's doing that, so he's interested in video, Sherlock Holmes video, it's a very fun thing. So we're trying, so currently, so people watch video, and then of course we record the neuronal activity. And first now we look for the brain, what are the relevant measures, which measures are encoding, we have different measures, and so on and so on. And then we want to apply those measures, let's say if there may be autocorrelation window, spectral entropy are relevant, maybe scale-free may not be relevant, but okay, just say it. Yeah? And then, now I lose my own movie here. Okay, and then we say, okay, then we want to apply the same measures to the movie. So what we have as voxels, so we do a whole brain voxel, we call these little functional units in the brain and fMRI voxels. and they're much smaller than the regions. And then we want to do the same for the pixel in the movie. So we create a time series of the pixel in the movies, and then I don't need to tell you what we can do. Yeah, and then I hope that we find some correspondence. Yeah, and I expect that the better the individual subject's brain, let's say, autocorrelation window, corresponds to the virtual autocorrelation window of the movie, the better the consciousness, the better the encoding. And the more ultimately, the more mutual information, that's something you can measure with the MI, mutual information between movie and brain, and the more likely you can become conscious of the damn thing. Yeah? So but that's a very tricky one. I agree with that. It's a good question. We also try to do the same for mental processes. We try to create a time series of mental processes, because that's what we need. Yeah? And remember what I said with the hard stuff? Same thing here. Same strategy. That's why I want to do the hard brains. Yeah? And of course then also we try to now with own thoughts create a time series. Yeah?
You're right.
Sorry, one last question. Can spontaneous brain spatial temporal patterns manifest itself in things like mind wandering and attentional deficits and stuff like that?
Yeah, so the first one, for sure, that's what we're testing now. So we have a task where we look how much the subject fluctuates, whether the thoughts are more of external, related to the world, or more related to the self. And interestingly, we find quite an interesting fluctuation. And we try to analyze that fluctuation now with some of the signal processing measures. And then we do the same for the spontaneous activity. Yeah. So I cannot show you that relationship, but that's exactly what I would argue. You have a similarity in spatial temporal pattern between your thoughts and your spontaneous activity. So I hope that maybe in 5 years, I can put you under the scanner and make a readout of your resting state and know what you think. Yeah? The fluctuations of your internal and external thought. That's what I need as a psychiatrist, and that's what you ultimately need for your artificial devices. Yeah? I'm not doing anything special. I'm doing what other disciplines do always. Yeah? From the chemical formula, you have a readout what kind of stuff that is. Yeah? That's what I'm trying to do, nothing else. And my currency is spatial temporal. Okay, 5 years on this day, 5 o'clock.
All right, I think your taxi is probably almost here. So we need to wrap this up. And let's give another pause.